Welcome to Catalyst Grid. My name is Kingsley Aimufua, lead scheduler with DC Nordics. Today, we are looking at the most complex automatic power control challenge on the entire Hyperscale campus. We are talking about 20 generators running in parallel. This is Series 2, Episode 8, 20 generators, campus power backup at scale. In Series 1, we looked at Iron Gate. Iron Gate had 4 generators in an N+1 arrangement, 3 running, 1 on standby. It was a relatively simple, standard parallel operation. At FULCRUM, however, the scale is vastly different. FULCRUM features 20 generators arranged in 4 groups of 5. Each group serves a specific data hall and its unique load profile. But all 20 generators share a common 11 kV bus, and each one must be capable of paralleling with the others within exactly 30 seconds of a grid failure. There is no margin for error. 20 diesel generators, 80 megawatts of backup power, running simultaneously, synchronized, load sharing. This requires absolute precision in control logic to protect the critical load. Let's look at the layout. The generator yard at FULCRUM covers approximately 1.5 hectares. It is the largest single plant compound on the campus, housing the heartbeat of our backup system. The sets are arranged in 4 rows of 5. Rows 1 and 2 serve halls DH1 and DH2, while rows 3 and 4 serve DH3 and DH4. It is a highly structured modular physical arrangement. A central 11 kV busbar room is positioned strategically between the rows. Each generator connects to this common bus via a dedicated circuit breaker. This is the electrical center of gravity. The bus is sectionalized per hall, but bus couplers allow any generator to supply any hall. This cross-connection capability provides the ultimate level of campus-wide redundancy and failover support. Acoustics are a critical planning condition for a site this large. Each generator has an attenuated enclosure, and we've installed 3-meter louver walls on the boundaries to maintain a strict noise target of 45 decibels. Exhaust risers are individual per unit, but combine into shared acoustic silencers for high-level discharge. Control is managed by individual AVRs and a master synchronizer at the central AMF building. To handle hyperscale loads safely, our generator specifications must be uncompromising. These are not standard standby units. They are built specifically for continuous prime-rated operation. We are using 20 MTU 4MW prime-rated generators. As we established in Series 1, prime rating is absolutely mandatory for data centers. They must be able to handle sustained loads during long-duration outages. By utilizing 11 kV output directly from the alternator, we connect straight to the hall distribution busbar. This completely eliminates the need for step-up transformers, improving efficiency and reducing failure points. Speed is vital to the bridging logic. We require the engines to be stable within 10 seconds and accepting full load within 12. This 100% step load acceptance is rigidly verified at factory acceptance testing. Fuel autonomy is a strict contractual obligation to CloudCore. We must maintain 72 hours of fuel at 80% campus load. That requires a 96,000-liter bulk storage system. The real technical challenge is synchronizing 20 generators to a common bus simultaneously. This requires matching voltage, frequency, and phase angle with absolute surgical precision. Let's look at the sequence. Upon mains failure detection, all 20 generators receive an automatic mains failure, or AMF, start signal simultaneously. Within 2 seconds, every single engine is cranking. By approximately 8 seconds, the first stable unit closes its breaker onto the dead 11 kV bus. This first unit immediately becomes the reference machine, setting the electrical parameters for the entire system. Once the bus is live, the subsequent machines begin to parallel. The synchronizer continuously checks the voltage, frequency, and phase angle. It closes the breakers only when they are within exact, predetermined tolerances. By approximately 25 seconds, we have a full complement on the bus. A master load sharing controller then divides the 85 megawatt load equally. Each machine carries exactly 5% of the total demand. To maintain N+1 redundancy during the run, 1 generator per hall group remains on the bus spinning unloaded. It is ready to pick up the load immediately and seamlessly if any duty unit trips. To support 20 prime-rated generators, we utilize a single centralized fuel farm. This central system feeds individual 2,000-liter day tanks on each unit via a continuous ring distribution main. We house 100,000 litres total in double-walled diesel tanks. A continuous fuel polishing system constantly removes water and sediment, ensuring the diesel remains stable and clean for emergency use. 4 electric transfer pumps in an N+1+1 configuration automatically fill the day tanks based on level sensors. Interstitial monitoring and underground leak detection provide an extra layer of environmental security. The generator yard is our highest fire risk zone on the campus. Due to the fuel load, our strategy focuses on absolute compartmentalization and highly redundant fire suppression systems. Each generator bay is a separate fire compartment, divided by 4-hour rated structural walls. Inside the enclosure, we have fixed CO2 suppression, while external drencher systems on the roofs provide secondary, fail-safe defense. Today's series signal, paralleling 20 generators in 25 seconds, isn't something you figure out on site. The AMF logic, synchronizer settings, and governor curves must be fully engineered and rigorously tested at the factory. In episode 9, we move to the 85 megawatt UPS system. We'll examine the 2N+1 modular architecture and explain exactly why lithium-ion LFP chemistry is the only acceptable choice for hyperscale bridging. Thank you for joining me on this deep dive into the FULCRUM backup power system. The physical scale is massive, but the engineering control must be absolutely precise. I am Kingsley Amufua. Don't forget to subscribe, like, share, and comment below. Your support helps us grow this technical engineering community and share these insights. I'll see you in the next episode. Thank you for watching Catalyst Grid, building the machine at Hyperscale. Stay safe and goodbye for now. This concludes our technical documentation on hyperscale backup power generation. This concludes our technical documentation on hyperscale backup power generation. This concludes our technical documentation on hyperscale backup power generation. This concludes our technical documentation on hyperscale backup power generation.